In theoretical physics, 8-dimensional geometric models are used to explain fundamental physical constants. But recently, a specific 8-dimensional structure, visualized here as a folding 600 cell, was translated into an executable Python script, and it started solving Bitcoin private keys. This script is powered by the G.O.D framework, which stands for Geometric Orthogonal Dialectics. The framework identifies a key's specific location by mapping it directly to the lattice structure. This process sidesteps the massive GPU clusters and computational overhead typically required for brute force hash attacks. Instead, the script takes the massive search space of an elliptic curve and maps it onto a finite 8-dimensional topological object known as a Clifford torus. To understand how this works, we need to trace the engine from its mathematical bedrock. We will start with pure 8-dimensional rotation planes, define the algebraic steering mechanisms that navigate them, and finally look at the actual Python code executing this attack on the SEC P256K1 curve. The following breakdown of this 8-dimensional geometry reveals how the framework translates abstract physics into a tool for active key recovery. To build this engine, we have to establish the foundational geometry of 8-dimensional space. In 3 dimensions, an object rotates around an axis. But in higher dimensions, rotation does not happen around an axis. It happens entirely within a 2D plane. As this diagram shows, 8-dimensional space contains exactly 28 independent rotation planes, one for every pair of coordinate axes. If we analyze the interactions between these 28 planes, we find exactly 378 possible pairs. They separate neatly into 2 data groups: 210 pairs that are orthogonal, meaning their rotations are entirely independent, and 168 pairs that are non-orthogonal, meaning they intersect and interact. That number, 168, is mathematically exact. It is the order of the Klein-Quartic group, and it dictates the total number of interacting degrees of freedom available in this space. From the initial 28 planes, the system scales using the divisor sum function, or the sigma chain. The sum of the divisors of 28 is 56. The divisors of 56 sum to 120. The divisors of 120 sum to 360. These represent the structural components of the E8 lattice. 56 is the exact population of the D8 root shell. 120 is the number of vertices on a 600 cell. 360 is the alternating group on the 6 lattice shells. The physical and cryptographic constants of this framework are not arbitrary parameters chosen by a programmer. They are deterministically forced by the strict number of ways 8-dimensional space is allowed to spin. If the 28 rotation planes define the space, we need a mechanism to navigate it. The engine achieves this through algebraic steering. The core navigational tool is the involution. In mathematics, an involution is simply an operation that is its own inverse. Apply it twice and you return to where you started. It acts as a perfect geometric mirror flip. At every level of the framework, the engine utilizes exactly 3 specific involutions. Together, they form what algebraists call a Klein foregroup, which is used to systematically divide the search space into measurable quadrants. These involutions operate on a specific topological stage. This diagram shows a Heegard splitting, a 3-sphere bisected internally by a rotating Clifford torus. This creates 2 distinct bulk regions inside the geometry. Inside the E8 lattice, the 240 coordinates divide precisely across this boundary. 112 classical roots, called D8, occupy one side. The remaining 128 quantum roots, called S+, occupy the other. The primary involution used by the engine is the cross-parity operator, known as sigma 29. When executed, it flips an observer's perspective directly across the toral boundary, moving cleanly between the D8 and S+ states. By using involutions to flip across this holographic boundary, the algorithm avoids searching an infinite coordinate space. It isolates specific data points by repeatedly having a finite geometry. These algebraic flips dictate the mechanical rhythm of the engine, driving a continuous 12-step orbital clock along the surface of the torus. 3 simultaneous tracking systems run on this clock: the left system operating at the E8 level, the right system at the Leech lattice level, and the spin system at the Craig lattice level. At moment 0, the clock starts. All 3 systems take an initial step. The magnitude and direction of that step are strictly determined by the geometry of the shell they are currently inhabiting. Immediately after, at moment 0.5, no movement occurs. Instead, Galois involutions shatter the data gathered from the previous step, dividing the reading into constrained, actionable pathways that will strictly dictate the trajectory of the next move. This process iterates, step by step, until we reach the critical juncture of the sequence, moment 6. Moment 6 is the Heegard point. It is the exact topological coordinate on the torus where the geometry forces a chirality flip, instantly reversing the direction of the orbit. Because of this forced reversal, the left and right tracking systems cross paths. For one step, they provide two simultaneous, opposing views of the exact same data point, creating a stereoscopic effect. The third system, spin, uses this stereoscopic depth to calculate the strongest signal resolution. It immediately adjusts its trajectory and locks on to the absolute target coordinate. The cycle concludes at moment 12. The orbit completes, and the internal Gare ratios of the systems compounding, and the coarse search grid transforms into a higher resolution net for the next pass. These are not three independent computational threads running in parallel. They form a single topological trap that tightens its resolution with every 12-step rotation. This 12-step theoretical orbit maps directly to the practical cryptography securing Bitcoin, the SEC-P256K1 elliptic curve. The curve possesses two inherent mathematical features that the framework exploits: the negation operator and the complex multiplication, or CM, endomorphism. The first mapping occurs here. The algebraic formula for elliptic curve negation is mathematically identical to the framework's cross-parity involution, sigma 29. The second mapping is the CM endomorphism. Its formula perfectly aligns with the boundary rotation involution, sigma 6. Because the curve's operators map perfectly to the Klein-4 group used by the framework, it is completely vulnerable to the engine's geometric division tactics. To execute this division, the script deploys tame, wild, and scout kangaroo walkers. These are standard algorithms from discrete logarithm attacks, repurposed here as physical agents walking the toral paths. The structure of the Bitcoin curve unwittingly mirrors the 8-dimensional geometry of the E8 lattice. This alignment allows the engine to repeatedly fold the curve's vast search space in half. This theory is executed in the Python script G.O.D trilateral attack. Here, the tame, wild, and scout roles are explicitly assigned to their geometric coordinates. As the script runs, it outputs its search space reduction metrics. The toral system calculates exactly how many orbital cycles it takes to divide the target area down to a solvable range. For puzzle 150, the algorithm applies the Mobius winding logic. Each level of the tower absorbs 12 bits of complexity through toral folding, stripping the 150-bit key down to an effective 29-bit search range. The computational speed of this script derives from its efficiency. It bypasses brute force, trusting the deterministic routing of the sigma chain to isolate the key. The pipeline is direct. 28 rotation planes define algebraic involutions. Those involutions steer a 12-step orbit, and that orbit isolates the key. The efficiency of the G.O.D engine suggests that the path to a private key is a matter of geometric resolution. High-dimensional folding determines the speed of the solve, making the recovery of a key a deterministic consequence of the geometry itself.